Now, let's review this old technique. If I give you y equal fx, you remember I told you the linearization means you're going to take the derivative and the fx equals fa, if this point is a, fa plus f prime a, x minus a. That's called the linearization. Basically, you are going to use the distance here on the straight line to approximate the distance on the curve. That's the delta y. And the one in the blue line is called the dy. It's right here. That's the old Taylor series of first degree. Well, if we got the multivariables, let's say you have two, x1, x2 as the function. So what you have? You change this straight line, and then you probably have this case. You have a surface, whatever shape, and then you approximate the surface by the tangent plane, and then what you use is the gradient to replace this derivative. So the linearization equals the height on the tangent point, on the same point, plus the gradient times the deviation, the change. So again, you use the change on the tangent plane to approximate the change on the curved surface. Clear? That have to be very clear. So that's the linearization. But we are talking about a function like this. You have n variables. Each point have n components. But you also have m components. Now, I'll give you an example. If I want to look at the gravitation field in any point in the space, you understand that the gravitation have direction. Go downward, eastward, upward, and then you need to give a vector function. This vector function has three variables, x, y, z, to tell you the position. So in such an example, like a gravitation field, you have the n equals 3 and the m also equals 3. So that's a little bit more complicated. But we still have the same concept of the linearization. What do we do? The linearization equals the function field at that particular point, you know, just plug it in, add, like this, the Jacobian matrix, multiply the vector of the difference. Here's the vector, but you put it into a column. So the Jacobian itself is m times n. And then this vector is n times 1. So in the end, this linearization, you really got how much? n straight line. You really got m of this. No, let me see, n or m. mn, yeah. You really got the n of those. Previous one, the gradient. So that's the Jacobian we learned in the first hour of this module. And this is where we need to use it. So anyway, the idea is, oh, you don't have a matrix. I can make a matrix. What a matrix? The Jacobian matrix. Replace this F. And you don't have a matrix here, H. I replace this H by the Jacobian matrix of the H. So that's the idea. Once you get the idea, let's look at the example. In the previous example, You remember we have this relationship, the y equals, no, actually, the x equals sine of y times t minus 1, that's the xt, and the yt is the frequency, that's not a change. And that relationship, if I take the derivative this to x, you see there's no x here, I get a 0. That's how we do the Jacobian matrix. If I take the derivative to y, there's y here, and then the t equal k, and then you get the k minus 1 here. That's the t minus 1. And then the y cosine, sine, take a derivative cosine, and then the y k minus 1, that's the y at the last step, that's one thing, and times the t minus 1, that's k minus 1. That's how you take it, the Jacobian. But the second one is easy. Y equal itself, take a derivative to x is 0, take a derivative to y, it's going to be 1, take a derivative to y. So in that case, the Jacobian of this function f is going to be this fk. That's the approximation of your function f, which is 0, 0, the derivative to y, the derivative to y. And that's the fk. Well, now let me write the relationship between the position on the sine wave. The xk equals the position before at, you remember the gradient talk about the change, and this change based on the previous position. And the y, you can see it clear, that's not a change. The y at the time k equal y k minus 1, 0 times this plus k minus 1. That's not change anyway. So that's the new relationship of the transition. What it means transition? It means to transform the position. Okay? And the wave really just follow the wave line, that's not a change of frequency. And well, you understand that we talked about the key difference. Oh, here you go. See, in the example 1, when this is not linear, what I made is the matrix, like this Jacobian matrix. Take the derivative of the first, take the derivative of the second, take the derivative of the third, and we got the 2 by 2 matrix. And that relationship is linear. It's exactly what you see in last lesson, but what? But this change, it's not a constant, because when the k change, this change. That's the problem. And then when the k change, this number change, this number change. In the previous lesson, this is completely a constant. You don't need to put this little k on the bottom, because you can put just 1f, good enough. But today, in each step, you need to calculate the Jacobian change at each time step. That's the difference. Okay, so what do? Oh, when you are not linear, we just use the Jacobian to linearize it. That's what we prepared. Well, let's look at another example.